Hello, everyone, and welcome to today's presentation. I'm excited to have you here. Today, we'll be exploring data representation in computers. This is the first slide, so I'd like to briefly introduce the topic. We'll look at how computers store and handle data, and why this is so fundamental. We'll cover key concepts that help us understand the digital world better. Let's get started. All right, let's take a look at what's inside the contents of this presentation. We'll start with the basics of how data is represented digitally. This includes understanding the binary representation, which is fundamental because computers process all information using only two states, on and off, or 1 and 0. Then, we'll explore various numbering systems, which help us interpret and convert data more effectively. Using doubling is an important concept here, as it's a simple way to understand how binary numbers grow and how we can convert decimal numbers into binary. We'll dive into the process of converting decimal numbers to binary, which is a key skill for anyone working with digital data. This ties into the broader theme of digital representation, where positional notation plays a crucial role. Positional notation is what allows us to understand the value of each digit based on its position within a number. Later on, we'll practice these conversions to solidify our understanding, ensuring that we can confidently handle decimal to binary conversions ourselves. Overall, this slide sets the stage for understanding how data is stored and manipulated in digital systems, which is essential for everything from basic computing to complex data processing. Let's start with the basics of how data is represented in digital systems. First, we have the concept of a bit. A bit is the most fundamental unit of information, and it can only have two possible values, 0 or 1. These two values are the building blocks of all digital data. Think of a bit as a simple on or off switch. Moving on, we have the byte. A byte is a larger unit of digital information, and it typically consists of 8 bits. So, when we combine 8 of these bits, we get a byte. This is a standard way of measuring and storing data in computers and telecommunications. Understanding these two concepts, bits and bytes, is crucial because they form the foundation of how data is stored, processed, and transmitted in digital systems. Everything from text and images to videos and software ultimately boils down to sequences of bits and bytes. This fundamental binary representation is what allows digital devices to communicate and operate seamlessly. Let's talk about digital representation. Within a computer, all information, whether it's text, images, or sounds, is stored in a digital binary format. Now, the key term here is bit, which is short for binary digit. A bit is the smallest piece of data a computer can handle. Unlike humans who interpret words and pictures, computers understand only patterns of bits. A bit can have only two possible values, a 1, which we write as 1, or a 0, written as 0. Think of it like a light switch, either it's on or off. These two states can represent simple conditions or choices, like whether a light is on or off, or a device is active or inactive. This binary system is fundamental because it allows computers to efficiently encode and interpret all kinds of information by just using these two states. So, understanding bits and how they represent two states is a crucial step in grasping how digital technology works overall. Let's take a closer look at numbering systems. Each system has a base, also known as a radix, which determines the number of unique symbols used. Starting with the binary system, which is base 2, it uses just two symbols, 0 and 1. Moving on to the decimal system, which is the one we're most familiar with, it has a base of 10 and uses digits from 0 through 9. Then there's the octal system, with a base of 8, using symbols from 0 to 7. Finally, we have hexadecimal, which is base 16, and it extends the symbols to include 0 through 9, and then A through F, where A equals 10, B equals 11, and so on up to F, which equals 15. Understanding these different numbering systems is fundamental because they form the foundation of how computers process and represent data. Recognizing how each system uses a different set of symbols and bases helps us see the big picture of digital systems and data encoding. Now, let's move on to the concept of using positional notation. This is a fundamental idea in number systems that really transforms how we understand and work with numbers. Essentially, positional notation means that the position of a digit within a number determines its value. For example, in the number 345, the 3 is in the hundreds place, the 4 in the tens, and the 5 in the ones. This system allows us to represent very large or very small numbers efficiently, simply by changing the digits' positions. It's the backbone of our decimal system, but it's also used in binary, octal, hexadecimal, and many other number systems. Recognizing how position impacts value helps us understand how computers process information and perform calculations. So, by mastering positional notation, we gain a powerful tool to work across various number systems and applications, linking directly back to our overall theme of understanding the fundamentals of digital systems. Let's walk through the steps to convert a binary number to a decimal. First, write down the binary number you want to convert. In this case, we'll use 10,011,011. Next, list the powers of 2 from right to left, starting at 20. So 20 is 1, then 21 is 2, 22 is 4, and so on, increasing the exponent by 1 each time. Since our binary number has 8 digits, we need 8 powers of 2, which are 128, 64, 32, 16, 8, 4, 2, and 1. Now write the binary digits below their corresponding powers of 2. So, the first digit, which is 1, goes below 128. The second digit, 0, goes below 64, and so on, aligning each binary digit with its respective power of 2. Next, connect each binary digit with its corresponding power of 2 by drawing lines from the digits to their related powers above. Start from the right and move leftward, linking each digit to its associated power. Then look at each digit again. If the digit is a 1, write the corresponding power of 2 below the line. If it's a 0, write 0 instead. This helps us identify which powers of 2 contribute to the final value. Finally, add up all the numbers written below the line. The sum of these values gives you the decimal equivalent of the binary number. For our example, the total is 155. To clearly indicate the base, write it as 15,510, showing that it's a decimal number. Now, let's talk about using doubling as a strategy. Doubling is a technique where you effectively increase your investment or effort to accelerate progress or improve outcomes. The key idea here is that by doubling down, you're committing more resources at the right moments, which can lead to faster growth or stronger results. It's important to highlight that doubling isn't just about blindly increasing your input. It requires careful timing and understanding of the situation. When used wisely, doubling can help you capitalize on momentum and push past obstacles that might otherwise slow you down. Throughout this presentation, we've emphasized the importance of strategic decision-making, and doubling is a powerful tool in that toolkit. Remember, the goal is to leverage doubling to maximize your potential without overextending yourself. So, keep this concept in mind as a way to reinforce your efforts when the opportunity is right. All right, let's walk through the steps to convert a binary number to decimal using the doubling method. First, write down the binary number you're working with. In this example, we'll use 10,110,011. Now, this method is nice because it doesn't rely on powers, which makes it simpler for mental conversions, especially with larger numbers. Starting from the left, you'll double your current total and then add the current digit. Think of it as building the number step by step. So you begin with 0, double it, and then add the first digit, which is 1. Next, double that total and add the next digit, which is 0, then double again and add 1, and so on. You repeat this process, doubling and adding, until you've gone through all the digits. This way, you're effectively shifting and accumulating the value in your head without needing to memorize powers of 2. Once you've processed all digits, you'll have your decimal equivalent. To clearly communicate the result, write it down along with its base, like 89 in base 10, which shows we're working in the decimal system. This method ties into our overall theme by highlighting a practical mental math approach to understanding how binary numbers translate into familiar decimal values. making digital concepts more accessible. Now, let's put our knowledge into practice. Take a moment to try converting these binary numbers: 11,010,011, 11,001, and 11,110,011. The key here is to understand how each of these binary sequences translates into decimal numbers. For example, 11,010,011 in binary equals 209 in decimal, 11,001 equals 25, and 11,110,011 equals 241. Recognizing these conversions is essential because it helps us see how data is represented and processed in digital systems. Remember, mastering these conversions connects directly to our overall goal of understanding how computers interpret information. So, take your time to practice, and don't worry. This step is crucial for building a solid foundation in digital data representation. All right, let's walk through how to convert a decimal number, like 25, into binary. The key idea here is to repeatedly divide the number by 2 and keep track of the remainders. So, starting with 25, we divide by 2, which gives us 12 with a remainder of 1. Then, we take 12 and divide by 2 again, resulting in 6 with a remainder of 0. Continuing this process, 6 divided by 2 gives us 3 with a remainder of 0, and 3 divided by 2 yields 1 with a remainder of 1. Finally, 1 divided by 2 gives us 0 with a remainder of 1. Now, the important part is to read these remainders in reverse order, from the last division to the first, and that gives us the binary equivalent. So, for 25, the remainders read backwards are 1, 1, 0, 0, 1, which forms 11,001. This process is fundamental because it shows how numbers are represented in the binary system, which is the backbone of digital computing. By understanding this step-by-step method, you can convert any decimal number into binary, connecting the concept directly to how computers process data at their most basic level. Now let's take a closer look at this table, which illustrates the process of converting a decimal number to binary. On the top row, we have the quotients at each step, starting from dividing by 16, then 8, 4, 2, and finally 1. The next row shows the remainders at each step, which are crucial because they form the binary digits. Notice that the quotient decreases as we divide, and the remainders tell us whether to put a 0 or a 1 in each position of the binary number. The multiplier row indicates the value assigned to each position in the binary number, starting from 16 down to 1. Now, the key point here is how we check the final result. If we multiply each binary digit by its corresponding multiplier and then sum all those products, we should get back to our original decimal number, which in this case is 25. And as you can see, 16 plus 8 plus 0 plus 0 plus 1 equals 25. This process highlights the fundamental relationship between decimal and binary systems. It demonstrates how binary digits, or bits, encode numerical values through these place values, and how the division method helps us extract those bits systematically. Understanding this conversion is essential, especially as it forms the backbone of how computers process and store data. All right, now let's put our knowledge to the test by converting these decimal numbers into binary. First up, we have 1. Converting 1 to binary is straightforward, it's just 1. Next, 19. To do this, we divide 19 by 2, keep track of the remainders, and read them in reverse order. Similarly, for 28, we repeat the process. Divide by 2, note remainders, and then read from bottom to top. Finally, 37. The same method applies, dividing by 2 repeatedly and tracking remainders. Once we have the binary equivalents, it's important to verify our answers by converting back to decimal. This checking step helps ensure accuracy and reinforces our understanding of how binary and decimal systems connect. Remember, mastering these conversions is fundamental because binary forms the basis of digital systems we use every day. So, practice these conversions regularly to become more confident and efficient in working between these number systems.